Everything you see, touch, and even think is built from something you can't even see. Welcome back to Spacetime Confessions, where weird meets science. So, what exactly is a particle? In physics, a particle is the smallest unit of matter or energy. Think of it as a tiny building block, but one that can act like a wave, a point, or something in between depending on who's watching. Yeah, quantum physics is shady like that. One common confusion many of us face is the idea that a particle can behave like both a wave and a particle. But to understand this properly, we must first realize we are not talking about everyday macroscopic objects, not something we can see, touch, or feel. And we are also not talking about waves like sound waves in the air. Instead, we are speaking about fundamental particles, microscopic entities that follow rules very different from our everyday experience. In our macroscopic world, objects display properties like mass and charge, but not wavelength or frequency. Because of this, we have grown used to thinking that particle and wave are two separate, exclusive concepts. However, at the level of fundamental particles, these two ideas are not mutually exclusive. In fact, both wave-like and particle-like properties can and do exist simultaneously. Understanding this shift from macroscopic intuition to microscopic reality is the first step into the world of quantum physics. Let's begin at the top. All particles in the universe can be split into two families: fundamental particles, the indivisible building blocks of everything, and composite particles, made from those fundamental particles. Fundamental particles come in two clans: bosons, the force carriers of the universe, and fermions, the ones that actually make up stuff. You, me, stars, pizza, cats, dogs, all fermions. Let's meet the bosons first, the invisible messengers of nature's forces. There are four types of boson, each carry the four fundamental forces of nature: electromagnetic force, strong nuclear force, weak nuclear force, and gravitational force. Without bosons, forces would be mute, and the universe? It would be completely out of sync. Fermions break down into two categories: leptons and quarks. There are 12 of them in total. 6 quarks and 6 leptons, organized into 3 generations. Alright, we've met the solo acts, the fundamental particles. But what happens when they team up? That's when the composite particles come into action. Among all the particles we've explored, there's one that stands apart, silent, unseen, but essential: the Higgs boson. Without it, the universe would be a ghost town, full of massless particles, zipping around at the speed of light, never forming stars, planets, or us. It is through this particle that all other particles gain mass. Well, except neutrinos. Before we zoom in, here's something you should know. All particles fall into two families: bosons and fermions. Think of fermions as the builders of matter. They're the bricks. Everything solid and touchable is made of fermions. Electrons, protons, neutrons all fall into this club. They follow the rule: no two identical fermions can sit in the same state, so they naturally repel stacking. On the other hand, bosons are the messengers. They carry forces between fermions. Photons bring us light. Gluons keep quarks glued. The Higgs boson? It gives mass. And bosons don't mind sharing. They can all chill in the same quantum state. And yes, even protons and neutrons are fermions. But they're not fundamental. They're made of 3 quarks each. You see, whether a particle is a fermion or boson depends on its spin, not whether it's made of smaller pieces. So in this weird subatomic world, a particle can be built from quarks and still be a fermion. Quarks are social, always found in groups held together by the strong force. They build up protons and neutrons. They're the only particles that carry something called color charge, which makes them obey the strangest rule in physics: they can never be seen alone. Leptons, like electrons and neutrinos, are loners. They don't carry color charge, so they don't feel the strong force. That's why your electrons are free to zip around atoms, rather than getting stuck together like quarks. So in short, fermions equals matter, bosons equals force, quarks stick together, and leptons roam free. Bosons are a type of fundamental particles that obey Bose-Einstein statistics and play a crucial role in the universe. Unlike fermions, which make up matter, bosons are often force carriers, meaning they mediate interactions between particles. Photons are the carriers of light and the electromagnetic force. Gluons hold quarks together inside protons and neutrons. W and Z bosons, responsible for the weak force which powers radioactive decay. And the hypothetical graviton, if proven, would explain gravity itself. Next up, fermions. These are the building blocks of everything we see, from stars to sandwiches. Fermions are divided into quarks and leptons. Let's start with leptons. Leptons are particles that don't feel the strong force, but they are deeply involved in nuclear and particle interactions. Electrons orbit atoms, they're the reason chemistry even exists. Neutrinos, ghostly, almost massless and barely interact with anything, but they're everywhere. Muons and tau, heavier cousins of the electron, unstable and short-lived, but crucial to the cosmic puzzle. So, leptons are participants in interactions. Quiet but powerful. Now for quarks. They make up protons and neutrons, and they come in 6 flavors. Up and down, the ones we're most familiar with, they make up everyday matter. Charm, strange, top and bottom. Heavier, rarer, and found in high-energy collisions. Quarks never exist alone. They always combine to form composite particles. They're the hidden architecture of matter. When quarks and other particles come together, they form composite particles, structures more complex than their elementary parts. There are 2 main types. Mesons, made of a quark and an antiquark. Baryons, made of 3 quarks, like protons and neutrons. These are fermions. These composites are how the universe builds structure, from the tiniest atoms to the biggest stars. But every particle has a mirror, an equal and opposite counterpart. Welcome to the world of antiparticles. Every fundamental particle, from electrons to quarks, has an antiparticle. Same mass but opposite charge and quantum properties. Electrons have positrons. Protons have antiprotons. Neutrons have antineutrons. Neutrinos have antineutrinos. Quarks have antiquarks. Even force carriers. The W and W bosons are antiparticles of each other. Photons and gluons? They are their own antiparticles. When a particle meets its twin, they annihilate, releasing pure energy. This isn't science fiction. It's how real technologies like PET scans work today. As we reach the end of this journey, we realize that the building blocks of our universe are far more complex, yet beautifully connected than what we experience in everyday life. Particles are not just tiny pieces of matter. They are players in a deeper quantum reality, where waves and particles merge, forces are carried by invisible messengers, and every particle has its own shadow. From fermions that form the structure of everything we see, to bosons that weave the forces of nature. Each particle plays a role in the grand design. Composite particles show how nature builds complexity from simplicity, while antiparticles hint at a deeper symmetry in the cosmos. And yet, this is only the surface. In the upcoming videos, we'll dive even deeper, exploring each particle, their properties, their mysteries, and their roles in shaping the universe we call home. This was just the beginning. The real adventure into the quantum world is just getting started. Until then, stay bright, stay curious, and remember, this is where weird meets science.